Hello, and welcome to this lecture on linear approximation and its applications. My name is Reza Feroseti, a member of Pattern Recognition Lab at Ferdowsi University of Mashhad, and I'm excited to share how this fundamental concept simplifies complex problems in mathematics and engineering. This is the first part of my videos about linearization. Let's start with some questions that you're gonna be able to answer by the end of watching this video. The first question is, how does linear approximation help us solve problems more easily? What is the Taylor series expansion and how it can be used in linear approximation? How do we obtain the equation of the tangent line? How can we approximate the function step by step near a specific point? And the last question is, how can we approximate the function with two variables or more? Let's explore these topics together. To answer the first questions, in applications, we may encounter difficulties in finding exact solutions to the problem. Often approximate solutions are acceptable within some tolerance. The simplest approximation of a function is given by a linear function. In this section, we will study how a differentiable function may be approximated by a linear function. We already know that the tangent line goes very close to the graph of the function. As you see here, this is the tangent line, this is the graph of the function, and this is the point of tangency. The tangent line describes the behavior of the function near this specific point better than any other line. So it makes sense to use the tangent line as a linear approximation to the graph. Alright, let's answer the second question. What is the Taylor series expansion and how it can be used in linear approximation? The Taylor series expansion expresses a function as an infinitive sum of terms, each derived from the function's derivatives at a specific point. As you see here, we've got a function f of x, and this is the first derivative of the function, this is the second one, and this is the third one. And it's an infinitive sum of terms with these 3 points. Uh, if the expansion is around a equals 0, it's called the Maclaurin series. So it's not too much different, just a equals to 0. Linear approximation is the simplest case of this series. It uses only the first derivative. So to use this series in linear approximation, we only need these two terms, and we just threw the other terms away. Okay, let's answer this basic question. How do we obtain the equation of the tangent line? To find the equation of the tangent line, we use the point-slope formula at point x equals to a, which is y equals to f of a plus f prime of a times x minus a. Here, f of a is the value of the function, and f prime of a is the value of the first derivative of the function at point x equals to a. As you see here, we've got the function graph with equation of y equals to f of x. And this is the tangent line, and this is its equation. So the tangent line approximates the function's behavior near x equals to a. As we see here, it simplifies calculations and provides valuable insights into the function's behavior. Alright, let's start with a simple example to see linear approximation in action. Suppose we want to approximate sine of x near x equals to 0. As we remember, the linear approximation formula for x equals to a is f of a plus f prime of a times x minus a, where f of x is sine of x and a is set to 0. So for sine of x, f prime of x equals to cosine of x, and if we set x to 0, we've got f prime of 0, which is 1. So here we set the slope to 1. And f of 0, which is sine of 0, equals to 0. So we set this to 0. And as long as a equals to 0, so this is 0. So the tangent line equation at point x equals to 0 is only L of x equals to x. Okay, let's analyze the first example visually. The blue curve is a graph of sine of x, and the red line is a graph of x. As you see, for values of x near x equals to 0, the blue curve, which is a graph of sine of x, is almost a linear function. So, in order to analyze it more easily, we can replace the blue curve with this tangent line with this equation. Okay, this was the first example. To see more challenging examples, you can see the next parts of my video. And also, to access my full paper, you can scan this QR code. Thank you for watching.